Hello Physics 1 students and welcome to the Prelab 3 video. Today we're going to be discussing free fall. So hopefully this slide looks familiar because we went over it last week. So these are the kinematics equations for free fall, and you'll notice that we only have the kinematics equations that are specific to the y direction, and that's because of course free fall is going to be taking place in the vertical, right? So we have our position equation, right? So we have y of t. This is equal to 1/2 ayt squared, where ay is our acceleration in the vertical, plus voyt, where voy is our initial velocity in the vertical, and then y naught, which is our starting position or our starting height in the vertical. Then we have our velocity equation, so velocity as a function of time. This is going to tell us what the velocity is at any given time, and this is equal to ay times t plus voy, okay, where ay is still our acceleration in the vertical and voy is still our initial velocity in the vertical. Last but not least, we have our acceleration, which is ay of t is equal to ay. If you recall, quadratic equations, second order magnitude equations, these are going to have accelerations that are constant, right? So you can see there's no t on the right-hand side of the equal sign, and that's no mistake because acceleration is constant. Therefore, no matter what value you were to plug in for t, you would still get the same acceleration out because it is constant. All right, so the purpose of this slide is just to give you some general advice for how to best set up your kinematics problems. So the first bit of advice is to keep them as simple as possible. So avoid working with all negative numbers, okay? And if not otherwise specified, set initial positions to 0. So I realize that it might be a little bit confusing just seeing this as words, but I'm going to go over this in the slides when we're doing the pre-lab practice problems and the examples. So this should become pretty clear. Then the other thing is draw pictures. And I want those pictures to include all relevant variables. So once you get to projectile motion, we are going to have motion in the x direction as well. But that would be your acceleration in the y, your acceleration in the x, your initial velocity in the y, your initial velocity in the x, your initial position in the y, your initial position in the x, your start time, your end time, your turn time, if it's relevant to the problem that you're doing, and your turn position, again, if it's relevant to the problem that you're doing. And then don't just label the values by themselves, actually write in what their values are, right? So most of the time you're going to get that ax is equal to 0, right? Typically there is no horizontal acceleration, but still report that the acceleration in the x direction is equal to 0. This is really helpful, especially when you're drawing a picture, because you'll have labeled your origin so you know which directions are positive and negative. And so this really helps you keep track of your signs. If you report what all your relevant variables are and what their associated values are, it really helps you to keep the signs straight. And that's honestly the place that most students go wrong, is they'll mix up the signs. And if you draw a picture, that'll really help you keep your work organized. And then the last thing is define negative and positive directions and define relevant origins. So as I was mentioning before, with reporting all of your variables, before you even report all your variables, you are going to want to define which direction is positive, which direction is negative, and then where your origin is, where your 0, point is. So this slide here is the most simple example of a free fall problem that you might see. So a problem might be worded as something like an object is dropped, and then they want you to figure out how long it takes to reach the ground, or how long it takes to travel a certain distance, or given a certain time, how far did it travel, etc., etc. Okay? But this is the simplest example, and that's because your object is dropped, which means you have no initial velocity. That's what dropped means. Also, another thing that they may say in the problem is it starts from rest, that also is the same thing as dropped. That's telling you that there's no initial velocity. On Earth, that's giving you the information about what the acceleration is in the vertical. So then if it tells you that it was on Earth, then you can easily assume that gravity is 9.8 meters per second squared. And then the last thing is they may or may not give you an origin. For this simple example, I'm saying that the problem didn't give you an origin. So as I mentioned in my advice on the previous slide, define that as 0. There's no sense adding extra numbers and muddying the waters if you don't have to. Um, in a similar vein, now there is all the motion is taking place in the downward direction, right? So I could define up as positive, but then I'd have to work with a bunch of negative numbers. And as I mentioned before, it's a lot easier to work with positive numbers, because you don't have to worry about forgetting the sign. And so I'm just going to define down as the positive direction in this case. That way I can work with all positive numbers. So this is, as I mentioned, I have no initial velocity, or my initial velocity is 0, and no origin. So all I'm left with is that first term, the 1/2 AYT squared. And so since I know it's taking place on Earth, I can simplify this to y of t is equal to 4.9t squared. So as you can see, this is a slightly more complex example. Now we have an object being thrown upward rather than just dropped. So that means that we have an initial velocity in the mix now. It is again on Earth, so we know that gravity is 9.8 meters per second squared. And the origin is once again unspecified, so we're going to set it equal to 0. Now, for this example, I'm going to say that the initial velocity is equal to 5.4 meters per second. If you have already done the pre-lab practice problems, you should understand why. It's going to look very similar to your pre-lab practice problems, which is exactly why I pulled that specific number. And then gravity, as we talked about before, it's taking place on Earth, so negative 9.81 meters per second squared. You can see from my drawing over here, no, I didn't label everything. When we do the pre-lab practice problems, I will be labeling absolutely everything, so you'll get to see a really good example of that. But I did label what direction is positive, right? So that means anything that's upward is going to be positive. So the ball or the object was thrown upward, so that means that VOY is a positive number, and gravity is going to be pulling this object back down. And so in this case, because of how we have defined our origin, this is going to be a negative number. So when I write my position equation out, I have negative 4.9t squared, right? Because half of 9.8 is 4.9, plus a positive 5.4t. So this is very similar to the problem that I just did, except this time we have an object being thrown downwards rather than upwards. So that's going to change how I choose to label my origin and which directions I choose to label as positive and negative. So I have a downward throw. I know that gravity is going to act in the downward direction. So in this case, I'm going to make my positive direction downward. And that's because I don't want to have to work with a bunch of negative numbers. That way I can't forget the sign somewhere and then make a small math error that leads me to the wrong answer, right? So once again, our origin is unspecified, so I'm going to set that equal to 0. So you can see here with our position equation, we just have the first two terms again, because as I mentioned, the origin is unspecified. Let's say for this example that the initial velocity downward is 0.4 meters per second. Again, if you've done the pre-lab practice problems, this number should look familiar to you. And gravity, as we've said many times before, is 9.81 meters per second squared. So when we plug this into the position equation, we get 4.9t squared, and that is positive, plus a positive 0.4t. Now, once we have this position equation, there's a lot that we can do with it. One of the questions that might be asked is, after 3 seconds, how far did the object travel? In which case, you would just plug in 3 seconds everywhere you see t, and then solve. And over here, that would give that number that you solve for would be how far the object traveled in 3 seconds. All right, so now let's look at the most complex example that we've done so far. So this time we're going to have all three terms. So we have an object that's thrown upward, it takes place on Earth, and it starts at a height of 2 meters above the ground. Okay, so that means we're going to have all three terms in our position equation. So 1/2 AYT squared plus VOYT plus Y naught. Now, once again, this is taking place on the planet Earth. So gravity is going to be 9.81 meters per second squared. And as you can see from my illustration here, I'm going to say that up is the positive direction, and the reason for that is because we do have an upward component of motion, and that is the initial velocity. So since we have a mix of upward and downward motion, I'm going to go ahead to the default and define upward as positive. Okay, so that means that gravity, which always acts downward, that is negative. But that also means that the velocity in the y direction is going to be a positive 5.4 meters per second. Yeah, I know I'm not creative. I'm using the same numbers again. And then the initial or the starting height is going to be 2 meters above the ground. Well, my origin 0, 0 is where the 0 is in the y direction, right? And then if I go up from there, that's going to be a positive number. So that's why this is positive 2 meters above the ground, right? Because I defined up as positive. And besides being a little bit more of a headache to solve, because of course this is a quadratic equation that is not easily foiled, and by foiled I mean factored, right? But with a problem like this, you could again be asked to solve for the final time, your final position, turning position, turn time, and again, this equation here, as well as the velocity equation, if you're doing the turn time, would be highly instrumental in finding that. So it is important that you know how to write out these equations given information in a problem. All right, without further ado, let's get to Prelab 3. So on the right-hand side, you can see the Prelab practice problems for the free fall lab. If you haven't already attempted these problems, I would highly recommend that you pause the video now and work your way through them, because you will see very similar problems to these on the quiz. And the more times you've worked through it and the more times you've seen the material, the better off you will be. All right, Prelab 3, problem 1. For a ball released from rest, dropped, as you can see, I have labeled up top that VOY is equal to 0 meters per second, right? Because I said that it could be rest or dropped. Those are indications in a word problem that you have an initial velocity of 0. Okay, so a ball released from rest or dropped, how much time will it take to fly through the first 3.5 meters? So right here, what we're trying to find is T final, okay? So since we're given a final position, we are going to be using our position equation, which is this guy right here, okay? And then we're going to want to draw a picture of our motion, okay? So we were told that the ball was released from rest, and we want to know how much time it's going to take to fly through the first 3.5 meters. They haven't given us an origin, so as you can see, I've just labeled that as 0. Then we're going to travel through 3.5 meters of motion, of free fall. Okay? As I mentioned before, the initial velocity is 0 meters per second. The gravity, because I'm defining down as the positive direction, so you can see here, this is my origin, okay, and going downward, that's going to be positive. So that means AY, or my acceleration in the vertical, which is gravity, is going to be a positive 9.8 meters per second squared. T initial is 0 seconds. No sense in complicating things and making it not 0. Makes the most sense for probably all the problems that you're going to do to set your initial time as 0 unless otherwise specified. And then last but not least, this is what we're solving for right here. That's T final. Okay. So here we've written out our position equation again. Now we're going to plug in our values from our picture. Okay. So this is going to be the only time that I actually put in the 1/2 times 9.8. Typically, I'm just going to simplify this right away to 4.9. But since it's the first problem, that's why I left that there so that you can see where that 4.9 came from. As we talked about, there is no initial velocity. It is 0, so 0t. And then there is no starting height, so I set it to 0. So this is also 0. Okay? Now, since both of these values are 0, they're going to go away, and more simply, we just have y of t is equal to 4.9t squared. So the next step is to realize that the final position, so 3.5 meters, is equal to y of t final, right? So if you plug t final into the position equation, into the right side of the equal sign, this should give you 3.5, right? Which is great because then we have one unknown and one equation, right? So we can just solve for t final. Okay, so that's what we're doing here, right? We divide both sides by 4.9 to get t final squared by itself. Then once we divide both sides by that, we get 0.714 is equal to t final squared. We take the square root of both sides, okay, and we get that t final is equal to 0.85 seconds. And if it's helpful for you to check your work, and I do recommend this if you have time to check your work on a graphing calculator, go ahead and plug in y of t is equal to 4.9t squared, or x squared if your calculator isn't on the up and up with t variables and it only does x, okay? So this would be what your graph would look like, right? Because I chose to define the downward direction as positive, right? So that's why our parabola is opening upwards. This is where I started, t initial, this is y initial, right, 0, 0. And this is the point that I found, right? So I wanted to find, I already knew that this was 3.5, right? So I wanted to find the t that was associated with 3.5, and that just so happens to be 0.85. All right, that's about it for problem 1. Moving on to problem 2. All right, pre-lab practice problem number 2. So this one's kind of a doozy, as you're going to see in a little bit, but the prompt says a ball is thrown upward with an initial speed of 5.4 meters per second. How far up will it rise? Now for this, we're not only going to need the position equation, but we are also going to need the velocity equation. Okay, so I'm going to draw my picture first, define all my variables. Okay, so you can see this is my object down here. It's starting at 0 meters, okay, because again, they did not give me a specific origin. They didn't give me a starting height in the prompt anywhere. And so I'm going to define my starting position as 0 meters. Okay, once again, my starting time is 0 seconds. I'm going to define upward as the positive direction. That's because this time I have mixed motion, right? So the ball is being thrown upward, or object is being thrown upward, but gravity is working downward, right? So since I have a mix, anytime that I have a mix in the directions of my motion, I am going to choose to define up as my positive direction. You don't have to do that, but that's how I do it. Okay, so as we saw in the problem, velocity, the initial velocity in the y direction is equal to 5.4 meters per second. And this is a positive number, right, because I'm defining up as the positive direction. Then that means that down is the negative direction, which means that gravity, or our acceleration in the y direction, is going to be negative 9.8 meters per second squared. What I'm trying to find is going to be y turn, but you're going to see in a minute that I'm going to need to find t turn before I can find what I'm looking for, which is y turn. Okay? Now, an important piece of information is the fact that at the top of the motion here, the velocity is going to be equal to 0. That's why, as I mentioned before, this time we're going to need the velocity equation. That's going to allow us to solve for t turn, which then will allow us to solve for y turn. Because if we try to solve right now, we don't have y turn or t turn, which means we would be working with one equation and two unknowns. And of course, you know that algebraically, you cannot do that. So we need to introduce a second equation to solve for our second unknown. Okay, so velocity equation, because we're solving for t turn first, we're going to plug in our values, right? As we established, acceleration negative 9.8 times t plus VOY, which is a positive 5.4. Okay, we're going to set that equal to 0, right? Because up here at the top of the motion, velocity is equal to 0. And we're going to solve for t, which is specifically going to be t turn. So we carry on, we move the negative 9.8 to this side of the equal side, it becomes positive. Divide both sides by 9.8. Then we find that t turn is equal to 0.55 seconds. Now we can move on to step 2 and start solving for y turn using t turn, right? So we're going to write out what our position equation is, because now we're looking for a position. Actually, that's what we were always looking for in problem 2, right? Y turn, so y of t is equal to negative 4.9t squared plus 5.4t plus 0. Remember, the origin was 0, so this term's going to go away. So y turn is equal to y of t turn, right? That's the definition of what it is. And so you can see I've plugged in t turn everywhere that I see t on the right-hand side of the equal sign. And then we plug in that actual value that we just solved for, so the numerical value of t turn. Otherwise, that wouldn't do us too much good. That would be the same problem as I was talking about before we solve for t turn, right? You can see here that we've got one equation and two unknowns, right? The y turn and t turn. But thankfully, we already solved for it. So we plug in that numerical value and we solve, and we get that y turn is equal to 1.5 meters. And then if you want to see what this would look like on the graphing calculator, you can see here, this is 0, 0, so this is our starting time and our starting position. And up here at the turn, so the maximum displacement, the highest that it goes, that's right here. And that point is t turn, comma y turn. Okay, and y turn was what we were solving for here. And you can see that it's about at 1.5. So like I said, it can be really helpful if you have time to plug it into your graphing calculator to make sure that you didn't make a math error and that you are in the right ballpark, right? Because we wouldn't know the difference between, 1.48 versus 1.5 if it was a small math error. But if you got 78 and you should have gotten 1.5, when you graph it, you'll be able to tell that you made a big mistake somewhere, right? So that's where the graphing calculator is really helpful for checking your work. All right, problem number 3. A ball is thrown upward with an initial speed of 5.4 meters per second. How much time will it take to reach the top point of the motion? And we are going to recall just the velocity equation, right? Because that's all we needed on the previous slide to solve for t turn. And that's what we're going to be solving for. Same picture as last time because all the information is the same. Okay. And as I mentioned, we're solving for t turn. Once again, same steps that we used on the previous slide. I'm not going to really go into too much detail because we've already discussed it, but you get that t turn is equal to 0.55 seconds. And then this time, if we're looking at the graphing calculator to confirm our answer, we can see that 0.5 is right here. And so it's just a little bit offset to the right of that. And so 0.55 definitely looks like it's about right. All right, pre-lab practice problem number 4. A ball is thrown downward with an initial speed of 0.4 meters per second. How far will it travel during the first 2.1 seconds? So this time, we're looking for a position. We want to know how far it traveled. Okay, so we're going to need our position equation. Ultimately, the variable, the way that I like to abbreviate it, is we were looking for the final position. What is the position at t final, which is 2.1 seconds? All right, so we're going to draw our picture. There we go. Once again, we do not have an origin that has been defined, so I'm going to set the origin equal to 0. Y final, that's what we're looking for. Initial velocity, they gave that to us. It is 0.4 meters per second. Now, since it's downward and gravity is downward, I'm going to define the downward direction as positive, as you can see right here. Okay, that way I don't have to work with a bunch of negative numbers. Okay, so that means the initial velocity is in fact a positive number, and gravity is also a positive number. Okay, the initial time, 0. The final time is 2.1 seconds, and that was given to us in the problem. All right, so let's get started. So we have our position equation. We're going to plug in the values that we have from our image over here. Then we know that y final is equal to y of t final, so we want to plug t final in, which is our 2.1 seconds, everywhere we see t on the right-hand side of the equal sign. And so you can see now instead of having t final over here, I've plugged in the numerical value 2.1. When we calculate that out, we end up getting that y final is equal to 22 meters. Also, if you wanted to check this on a graphing calculator, this is what your graph would look like. Remember that I set the downward direction as the positive direction, so that's why my parabola is opening upwards, because my equation, if you recall, is just a positive 4.9t squared plus 0.4t, and so that's what this graph represents here. Now the point of interest is y final, so I was told that t final was equal to 2.1, and so then I'm looking for the corresponding value over here. Okay, and so you can see if we go up from 2, so this is about the 2 mark here on this line. It's a little bit over to the right, just a smidgen, and you can see that this x is up by 22, right? And that's exactly the value that we got. So once again, if you're using your graphing calculator to confirm, everything checks out here. All right, pre-lab practice problem number 5. So an object is constantly accelerated from rest. So that means that our initial velocity is going to be equal to 0. If it reaches a distance of 2.8 meters in 1.2 seconds, what is the acceleration? So this time we're going to be solving for the acceleration. And since we've been doing a lot of free fall and this isn't necessarily a free fall problem, I decided to put everything in the x plane. Okay, so we're going to be solving as if this is horizontal motion. So first things first, let's draw our picture. Okay, so here's our object, and I'm defining to the right as our positive direction. We are starting at a position of 0 meters, since in the problem, nowhere do they define that there is a specific starting position. So I'm going to keep it as simple as possible with 0 meters. Our starting time is 0 seconds. And then our finishing position and our finishing time are 2.8 and 1.2 respectively, as stated in the word problem. And then to reiterate what I have up here, the initial velocity is 0 meters per second since we're starting from rest, and our unknown is ax, right? So that's what we're going to be solving for. Okay, so I'm going to rewrite our position equation, then plug in what we do know. So we know that the initial velocity is 0, and we know that the initial position is 0. So that simplifies to x of t is equal to 1/2 axt squared. So right now you may be thinking to yourself, well, there are several unknowns and one equation, but the good thing is we do actually have 2 of these 3 unknowns, right, that we can plug in. So x final, we were given that was 2.8 meters, and t final, we were also given that was 1.2 seconds, right? So if we plug those values in, then we would just have 1/2 ax times t final squared, which would be 1.2 seconds, and that would be equal to 2.8 meters, okay? So you can see that's what I've done here. Now I'm just going to eliminate this little intermediary step just to make it a little more simple to look at. So we have 2.8 is equal to 1/2 ax times 1.2 squared, okay? So we square our 1.2, right, because it's an exponent, so we should work with that first. So we get 1.44. Then we multiply both sides by 2 so that we can get rid of this fraction over here. So once we do that, we have 5.6 is equal to 1.44a, or a times 1.44, same. So we have, then we want to get ax by itself, right? So we divide both sides by 1.44, so 5.6 divided by 1.44 is equal to 3.9 meters per second squared, and that is our final answer for ax. All right, we're coming down the home stretch here. Second to last problem, problem number 6. A ball is thrown upward with an initial speed of 5.4 meters per second. How long will it take the ball to return to the starting point? So the important thing here is our position equation in the y, and we are looking for the second time that the position is 0 meters. So that's why I have t subscript 0 meters, because we're looking for the second time that the position is at 0 meters. Because remember, when we toss the ball, since there isn't a specified origin in this problem, we're going to start it at 0 meters, but we want to know when it returns to that point. Okay? So I'm going to actually put our graph in here just to start off with, because I think that's the easiest way to visualize this problem. So we're starting at 0, 0, and we want to know what this time is here, right? We want to know how long will it take the ball to return to the starting point. So we have a time and a position. We know that this position is 0 meters, right? So we want to know what that other time is associated with the position 0 meters. Okay? So let's get started. So we plug in the values that we know. You can see I've defined everything down here, right? I've defined up as positive, down as negative. That's why our initial velocity is positive, and that's why acceleration is negative. So negative 4.9 t squared plus a positive 5.4 t. We started at 0, 0, so our starting height is 0. Now, we're going to set this equal to 0, right? Because we want to know what the times are, right? Because we're solving for how long. We're solving for a time. We want to know how long it's going to take before it returns to the starting point. Well, we know the starting point is 0 meters. That's why I set this equal to 0 meters, because this represents our position, right? So this is 0 meters. We set that equal to negative 4.9 t subscript 0 meters squared plus 5.4 t subscript 0 meters. And then, of course, we have this 0 here, just placeholder 0, right? So what we're going to need to do is we're going to need to factor. Thankfully, this is an easy equation to factor. Otherwise, we would have to use the quadratic equation, the negative b plus or minus the square root of b squared minus 4ac all over 2a. That business. Thankfully, we don't have to do that yet because we can easily factor this. So we factor out this first one, and so we know that this first root is going to be 0, right? It's 0, and we can see that right here on the graph. It does intersect at 0, 0. So yeah, that makes sense. However, that's not the point that we're interested in. We want to know how long it takes to return to the starting point. As I've said multiple times, this is the t at 0 meters that we're interested in, right? So now we have to solve this one, okay? So that's what we're going to do. So we solve for this. We move our negative 4.9 to the other side of the equal sign, so now it's a positive 4.9t. That's equal to 5.4. Divide both sides by 4.9, and we get that the other point, the one that we're interested in, is 1.1 seconds. And if we come over here and we look at our handy dandy graph, we can see that just past 1 on the t-axis, that is indeed where our point is, and so this makes sense. All right, we made it. Prelab practice problem number 7. A ball dropped from the roof of a building reached the ground in 3 seconds. How tall is the building? So recall that our position equation in the y direction is this guy right here, and we're going to be looking for y final. We're looking for our final position. So first things first, let's draw our diagram using the information that they gave us in the word problem. So we know that the ball is being dropped, right? So that means that our initial velocity is equal to 0 meters per second. It also means that we don't have an upward component to our motion. We just have gravity acting on this downward, and the object is free falling. And so for me, it makes sense to define down as the positive direction. That way I don't have to work with a bunch of negative numbers. So AY, or our acceleration in the vertical, is going to be equal to a positive 9.8 meters per second squared, since it is in the downward direction, and the downward direction is defined as positive. Moving on to our starting height, or our starting position in the y direction. Also, they don't specify that in the word problem, so as I've been doing many other times before in the other problems, I'm going to set that equal to 0 to keep it as simple as possible. Our starting time is 0 seconds. Our ending time is 3 seconds, as stated in the problem, and we are looking for y final. So essentially what we're finding here is what is the displacement over these 3 seconds, right? And that'll give me what the height of the building is. All right, well, let's get down to business. So we have our position equation, We plug in the values that we know, right? 4.9t squared plus 0t, right? Because our initial velocity is equal to 0, plus 0 because our starting height is also equal to 0. We can simplify that to just be 4.9t squared. Then we know that y final is equal to y of t final, which is equal to 4.9 t final squared. We know that t final is equal to 3, so we're going to plug in 3 where we see t final. So we have y final is equal to y of 3, which is equal to 4.9 times 3 squared, right? 3, this is t final, right? This is t final. We've just plugged in the value they gave us. And we get that y final is equal to 44.1 meters. So that's how tall the building is. The building is 44.1 meters high. All right, so quiz 3 is going to be very similar to quiz 2 in that there are going to be 5 multiple choice questions from the topic we covered this week, and there will be 5 multiple choice questions from the topic last week. Okay, so the 5 multiple choice questions from this week are going to be based on the free fall pre-lab practice problems that we just went through. The 5 multiple choice questions from last week are going to be based on the kinematics topics that we covered last week. So we're talking distance, displacement, speed, and velocity. Okay. If you need to brush up on the kinematics from last week, I am going to go through some review, but if you feel really comfortable with that topic, then feel free to stop the video here. Alrighty, so if you're still here, that means that you want to review the materials from last week from kinematics. So without further ado, let's get started. So as you can see here, I have a position and velocity versus adjusted time graph. So you can see that the y-axis is being shared by both position and velocity, but on the x-axis, we just have adjusted time. So I'm going to suggest that you pause the video here and work through all of the questions that I have posed on the right-hand side. So labeling all of these terms and finding the values for these terms, and then also labeling these and then answering this last question here. Once you're finished working through all these problems and these labels yourself, then go ahead and press play and move on to the answer slide to make sure that you got everything correct. All right, so hopefully you took some time and you worked through this on your own. So now I'm going to go through all of the answers. So first we're going to figure out where T initial, T turn, and T final are. So T initial is going to be this first point over here. Okay, so it's 0. T final is this last point here where the graph ends, and T turn is going to be this point here at the top point of my curve. If I had a data table, I would look at the largest position number, okay, because that's going to have the biggest displacement from my origin. Okay, that's how we define where that turnaround position is, right? Because over here on the left-hand side of the graph, we are moving in one direction, and then right here at this turnaround point is where we change directions and we start moving back in the other direction from whence we came, right? Because over here you can see that we start out at just, I don't know, maybe around a little bit below 0.5, right? And then we're coming up and maybe we're going up to like 0.7 or something here, okay? And then we go back down to 0.5, okay? So this point of maximum displacement, this is where the turnaround is. Now let's label y initial, y turn, and y final. So we kind of gave away what y final is, right? We've kind of harped on that's the maximum displacement, okay? Then y initial, that's going to be our position on the y-axis where we started. Y final, if we follow this dotted line here, it's about the same spot as y initial. So y initial and y final are approximately the same in this case. Then we're going to use the equations. So first we're going to use the position equation, okay? So please use the position equation to find AY. So we know that this term in front of the t squared term is 1/2 a. So we need to multiply this coefficient by 2 in order to get the acceleration. So 2 times 3.21 gives us a negative 6.42 meters per second squared. We know the coefficient in front of the t term is the initial velocity. So initial velocity is 1.99 meters per second. And then we know that the constant is our starting position, so y naught is equal to 0.41 meters. So that means we started 0.41 meters above the ground, or above the origin. Then we're going to use the velocity equation to find AY and VOY. So this is our velocity equation here. We know that the velocity equation is equal to AT plus VO. So the coefficient in front of the t term for the velocity equation is going to give us the acceleration, so negative 6.42 meters per second squared. And the constant in the velocity equation is our initial velocity. So our initial velocity is 1.99 meters per second. Then we're going to label a couple things. So on the position graph, label where the velocity is equal to 0 meters per second. Okay, so you can see this little x here is labeled 1. So this right here, this little x is where the position graph, where the velocity is equal to 0, right? And we know that by looking at the velocity graph here, right? And so this ties into number 2 on the velocity graph, where is velocity equal to 0? Well, you can see that this is where it's intersecting 0, right? This is 0 right here. So the point directly above it, since for number 1 we asked about the position graph, the point directly above it, if you follow the dotted lines, that is where the velocity is equal to 0 on the position graph. And of course, we know that to be the point y turn, right? And of course, the corresponding point on the x-axis is t turn. And then question number 3 says, what do they have in common? So what they have in common here is t turn, right? They both share that same time. They have a different x value, right? Because in the case of the velocity, it's going to be 0 at comma t turn, right? Well, I said that backwards, right? Because t turn is the x-axis. So it'd be t turn comma 0, right? Because it's x comma y. But up here, we would have our t turn comma y turn, right? But in both cases, both of these x's are sharing the point t turn. All right, so now I'm going to move on to a kinematics review of the equations that we talked about last week, as well as an example of the calculations that you did in the lab last week. All right, so here's a summary of all the kinematics equations that we discussed in the pre-lab last week. So we have distance, displacement, speed, average velocity, instantaneous velocity. Now remember, with instantaneous velocity, there are 2 different ways that you can calculate it, and the way that you calculate it depends on what information you're given, okay? If you have a graph, then you're going to draw a tangent line, tangent at the point t instantaneous that they give you. So say if it's t is equal to 2 seconds, that's what they want to know the velocity for, then you would draw a tangent line at t is equal to 2 seconds and then find the slope of that tangent line. Or if you're given the equation, then you would plug t instantaneous into the v of t equation. And then last but not least, acceleration. So that's the change in velocity over the change in time. So you can see here, this looks a lot like the lab that we did. So there's some data over here that looks just like the capstone data that we captured last week. And then these tables should look very familiar. These first 2 tables should look very familiar from the lab last week because they're the first 2 tables, right? This last one, this is just to make sure that you understand instantaneous velocity and magnitude. But I'm going to recommend that you pause the video here, work your way through these 3 tables, and then resume the video once you've finished and check your answers against mine. All right, so hopefully you took a few minutes and worked your way through all these problems, and hopefully you also got the same answers as I did, but I'm going to go through all of the problems. So the first thing is this first table here. We want our initial time, our turn time, and our final time. Now, you can see up here that I'm specifically requesting for the time interval from 0.1 seconds to 0.5 seconds. Now, you'll remember me stating in the video last week that when you get to quizzes and exams, a lot of times they won't go with the entire time interval, so that's why you really need to pay attention to the time interval. So this is actually really good practice for quizzes and exams right here. So you can see I've labeled them on my data table, and this data table should look really familiar. It looks a lot like the capstone data that you collected last week. So my initial time is 0.1, right? So I recorded 0.1. My final time is 0.5, so I record 0.5. And my turn time, I recorded as 0.30. So I chose to use the first one for my maximum displacement. And of course, when you're looking for your turn time, you want to look for the largest number on your position column, right? So your maximum displacement. And you can see that there are two of them here, right? I could have chosen 0.3. I could have chosen 0.32. I could have even approximated between the two and chosen 0.31. I chose to do 0.30, but if you filled in 0.31 or 0.32, both of those would be correct, okay? However, for all the other problems, this won't be present in your calculation, so this should be the only number that's different, okay? And like I said, the only other options are 0.31 and 0.32. So for position, we're going to look for our initial position, and that should correspond to our initial time. So our initial time is 0.1, the initial position is 0.17, so I recorded that there. For my final position, well, my final time is 0.5. The corresponding position is 0.192, so I record that there. And then for my turn position, I'm just going to look at what the displacement is, so what my position is at my chosen turn time, which is 0.3, so that's 0.309. So you can see I have 0.309. Now we come into table number 2. And we have the distance traveled. So remember, the distance traveled is going to be the absolute value of your final position minus your turn position plus the absolute value of your initial position minus your turn position, right? So essentially what's going to happen is you're going to have this cell minus this cell, take the absolute value, then this cell minus this cell, take the absolute value, and you should get 0.256. For displacement, you're just going to do your final position minus your initial position, so just 0.192 minus 0.17, and you should end up with 0.022. For the average speed, that's going to be distance over time, so you're going to take the value in here, so 0.256, and you're going to divide it by 0.4, right? Because that would be 0.5 minus 0.1, so that's your time interval is 0.4. And you should end up with 0.640. Then for the average velocity, that's going to be your displacement over time. So that's going to be this value here, so 0.022 divided by your time interval, which is again 0.4 seconds. So it's 0.022 divided by 0.4, and you should get 0.055 meters per second. All right, last but not least, instantaneous velocity. And the reason that I chose to do a problem like this is because we haven't really done a problem where you're just given a data table and asked to find the instantaneous velocity. We've talked about how to find the instantaneous velocity when you're given a graph and you draw the tangent line. And we've also talked about how to find instantaneous velocity when you're given the equation, the trend line equation, right? But if you have a table of information and you don't have a means to graph it so that you can find a trend line, then the next best thing that you can do for the instantaneous velocity is to use the points that are on either side of it, okay? And essentially do what you would do for a graph, but instead of drawing the tangent line, you would use the points on either side of your desired t instantaneous. Okay, so in this case, we want to know what the instantaneous velocity is at 0.35. So that's going to be this point here. Okay, and as we've talked about before, instantaneous velocity is going to be computing the change in position over the change in time. So what I was saying just now is I would essentially, since it's going to be between 0.36 and 0.34, I would use these 2 points. So I would use 0.36 and 0.301 and 0.34 and 0.306, right? And I would set up my slope equation. So essentially what I would have is I would have 0.301 minus 0.306 divided by 0.36 minus 0.34, okay? And once you do that calculation, you would end up with a negative 0.25. And then if I wanted to know the magnitude of the instantaneous velocity, as we've talked about before, magnitude means I just take the absolute value of it. So the magnitude of the instantaneous velocity at 0.35 seconds is 0.25. All right, well, that's about all I've got. So now we've reviewed kinematics and free fall. So best of luck on quiz 3.